let's talk about magnetism. And specifically, we are going to focus on this statement that magnetism is just a relativistic phenomena. That's it. And which is actually pretty true, right? So the classical electrodynamics is compatible with special relativity, and so what that implies is that we can then use the Maxwell's equations and Lorentz force law, and they can be applied in any inertial system, right? Now, what we shall see is that what one observer interprets as the electrical force, the other observer will regard as a magnetic force, so-called. However, the actual motion of the particle that they will predict will be identical, right? Okay, so now let's start off with the assumption that we have never heard of something that is called magnetism, right? So we only have electricity at our hands, right? Okay, so now we will consider a string of positive charges that are going to be moving towards the right with a velocity positive v, and negative charges moving towards the left with some negative v velocity, right? And at some distance r, there is then going to be a point charge q that is also traveling to the right hand side at speeds that is u, which is less than the speed v, right? Okay, so let me actually quickly draw this over here, right? So what I'm saying is that we have this line of charges, right? And there are positive charges up here, and I have negative charges over here, right? Okay, and so the positive charges are moving towards this direction with velocity plus v, right? And negative charges are moving towards this direction with velocity minus v. And at a distance r, right, we have another charge q, right? So this is the charge q that is moving towards the right hand side with some velocity u. Okay, so now we are also going to say that the charges are extremely close, so that we can then think of them as continuous line charges with densities of, let me write it down, they have positive, negative, plus minus lambda. So this is actually the charge density, right? Charge density. So the positive charges will obviously carry positive lambda charge density, and negative charges will have negative lambda charge density. Right. Now let's see what would be the electrical force in this particular scenario. That is the rest frame of the wire, right? Okay, let me move on to the next page. Now, for a stationary observer in a frame S. Now, the frame S is a frame that is for the stationary observer, right? Okay, so let's see what would be the electric field, right? So recall that your electric field, magnitude of your electric field is actually equal to lambda over 2 pi epsilon naught times r, right? And this is actually a very good approximation for all the fields, for the fields that are close to the line charge, right? So with this then, we have, also remember that we have our lambdas as plus lambda for the positive line of charges and negative lambda for the negative line of charges, right? So now to find the total field, what we have to do is then we have to sum over both of these fields. So we can take 1 over 2 pi epsilon naught r outside, and in lambda we would have first plus lambda, and then for the other one we would have negative lambda. And you can see from here that this thing goes to 0, and so the electric field would go to 0. And if the electric field goes to 0, then that implies that the force experienced for the stationary observer is also going to be 0, right? So this is for the stationary observer. Well, now let's consider the same situation from the point of view of an observer who is in the frame S prime. That is the frame that is moving towards the right hand side with speed u, right? So we are particularly talking about the charge q now. So let's go to this page, right? And so actually this is this diagram, refer to this diagram. We are talking about charge q now as the frame S prime, right? So that would be in frame S prime, right? Okay, so now the velocity of the positive charge, actually let me go back to this diagram, right? The velocity of the positive charges is smaller than the velocity of the negative charges in the case of this q, right? When we are talking about the moving frame that is of q. And that is because of the relative velocity, right? So then the Lorentz contraction of the spacing between the negative charges would be extremely high compared to the positive charges, right? Because then the negative charges would be moving really fast, really fast, in fact, and the spacing between these, there would be some Lorentz contraction over there, so the spacing would contract, right? And compared to the positive charges, they would be severely contracted, right? The spacing would be severely contracted for the negative charges. And so therefore the wire in this frame will carry a net negative charge, right? Because the negative charge density would be much higher than the positive charge density. And so what that means is then there must be some electrical force on this charge. And so I will now derive, and let me go here. I will now derive the Lorentz force using only electrostatics. And of course, there would be some series of relativistic transformations as well, right? So we are totally not talking about magnetism right now. We don't know what magnetism is at all, okay? But what we do know is electricity, and we know that there is something called special relativity, and the particles may feel relativistic effects when they're moving very fast, right? Okay, so note that now what I'll call the original frame as S, in which the charge Q is moving with velocity U. And the new frame S prime, that is the transformation frame, right? Now from the Einstein's velocity addition rule of velocities of the positive and negative charges in the S prime frame can be written as, let me write it down over here. So your V positive, that is the velocity for the positive charges, can be written as V minus U over 1 minus V times U over C squared. So I have written this thing using the Einstein's addition rule, right, for the velocities. And here again let me mention this, that V plus or V subscript plus is just the velocity of the charges that are moving towards the right hand side, right? And similarly for V minus, we would have V plus U over under the root, actually there would be no under root, sorry, 1 plus V times U over C squared. Right, so this is now the velocity of the particles or the charges that are moving towards the left hand side, right? Okay, now if say lambda naught, right, this thing over here, sorry, lambda naught is the charge density of the line charge in its own rest frame. Then for the positive and negative charges, we would have the charge density as follows, right? So I'm going to write it for both positive and negative, would then be plus minus gamma, that is for positive and negative velocities, times your lambda naught, right? So this essentially is the transformation, right, for your density of the charges, right? Okay, so here your this thing gamma plus minus is the usual Lorentz factor, right? So it is defined as, we have plus minus over here, so that simply means that we would have some plus minus velocities, right? So 1 over under root 1 minus v plus or minus squared over c squared, right? So now this is your Lorentz factor, right? Right. So now let's see what would happen to the net charge in the S prime frame. That would just be the sum of the charge densities, that is lambda plus and lambda minus, right? And so let's go ahead and let me write that down here. So the net charge, I'm going to say lambda total, right, is equal to then your lambda plus lambda minus, right? But we just wrote earlier that your lambda plus minus is actually let me write it down again. Lambda plus minus is equal to plus minus gamma plus minus, which is again your Lorentz factor for plus minus velocities, times your lambda naught, right? Well, and again the lambda naught is the charge density of the line charge in its own rest frame, right? Okay, so what I mean by that is that think of it as you are that line of charge, and then that lambda naught is the charge density that you yourself would see, right? So you are that line of charge, and the charge density that you would observe is then the lambda naught, right? Okay. So with this in mind, then we can write our total charge density as being equal to okay, so first I'm going to use this for the plus, and then I'm going to use it for the negative lambda, right? So for the plus, I would have gamma plus gamma plus actually lambda naught. For the negative lambda, I would have negative gamma minus lambda naught, right? Of course. Okay, so we could then see clearly that lambda naught could be then factored out, and so then your total charge density would be equal to lambda naught times gamma plus minus gamma minus, right? Okay, now we shall work out the Lorentz factor for these plus and negative charges. So we should work out these two things over here. So that's our next task, right? And remember, our goal is to see that if we can derive the magnetic force or magnetism just by using the concept of electricity and special relativity or relativistic mechanics, right? Okay, so let me go to the next page, and I write down my gamma plus, which is 1 over, so this is, remember again, this is just the Lorentz factor, that is 1 minus v plus squared over c squared, right? But now we know that our v plus from the Einstein's addition rule for the velocities is v minus u over 1 minus v times u over c squared, right? Okay, so then we can write our gamma plus as equal to 1 over we would have an under root, right? And 1 minus, now we're going to replace v plus square, right, with this thing over here. So we'll square this and put it back in here. So first let's write this 1 over c squared, this thing outside, right? And we would have inside v minus u over 1 minus v times u over c squared, yeah, and we would close the brackets and square, right? So the square root is all of this, right? So then this thing over here is my gamma plus, right? Okay, let me just get rid of that. Yeah, right. Now I will solve for this denominator term over here inside the square root, and so we will simplify that and we will write it down later on, and we'll substitute it back in this equation, right? So let me go ahead and do that on the next page. Right, so I have in the denominator inside my square root, the term I have is 1 minus 1 over c squared times v minus u over 1 minus v times u over c squared, right? And the square of this expression right here. Okay, so then this thing can then be simplified to, if we can factor out this c squared outside, and once we do that, but because we have this square over all of this term over here, right? So the term that would actually come out is c power 4, right? And so let's write that down over here. So we would have 1 over c squared as it is, and then again divided by c4, right? So we have just factored out this over here, so it comes out in the division symbol, right? Okay, so yeah, the next term or the term next to it would be v minus u squared, right, over, now we have factored out c squared from in, right? So we would have c squared over here minus v times u whole squared, right? Now let me again mention that we actually factored out c squared, but because c squared and this term, complete term over here, actually had this square on it, right? So what actually came out was c power 4, right? So it's a basic algebra, right? Okay, so let's move on, and then this whole thing over here would then be equal to further 1 minus v minus u squared times c squared, right? Because this c squared will cancel with this 4 and make it 2, and this will then go upstairs, right? That's pretty obvious. Okay, so c squared over, we would have in the denominator obviously this term over here, right? So that's c squared minus v times u whole squared. So we are just doing some silly mathematics right now, and eventually at the end of this lecture you would see what I think as a most beautiful result of nature, right? Okay, so let's continue. We have over here c squared minus v times u whole squared. All I'm doing is now taking the what you call LCM of this thing over here, right? So doing that, I would have now minus c squared times v minus u whole squared over obviously c squared minus v times u whole squared. Okay, so we can go ahead and expand this further by opening the squares, right, in the numerator. And so once we do that, what we would have is c power 4. Actually, let me get rid of this line over here, right? And let me utilize space properly. Okay, so I would have c power 4 plus, again, I'm opening these squares and these terms in the numerator, right? Okay. So I have c power 4 in brackets, right, plus v squared times u squared minus c2 minus 2 times c squared times v u. Okay, and then for the next term I have negative c squared I have outside, but inside let me open the square, that is v minus u squared. That would simply be v squared plus u squared minus 2vu. And not to forget the term in the denominator, that is c squared minus v times u squared. Again, let me just mention this, that u is the velocity of that charge that I placed outside that line of charges, that was charge q, and v is the velocity for the line of charges, right? Okay, so let's move on, and what you can see is that this term over here would cancel out with this term over here when I multiply this c squared inside, right? So this term we have as negative 2c squared v times u, and this negative c squared multiplied by this term over here would then give me positive 2c squared v times u. And so positive, negative, same magnitudes, they would, but opposite, say directions or signs, they would cancel out, right? Okay, so let's move on and write this expression that we have as now c power 4 plus v squared u squared minus v squared c squared minus u squared times c squared, and in the denominator again we have c squared minus v times u whole squared. Right. Okay, so what we can then see from here in the numerator, from the second and the third term, right, there are total 4 terms in the numerator, but the second and third term I can factor out my v squared, right? So what I would be having is then c power 4 plus v squared times u squared minus c squared, closing the brackets now, minus u squared c squared. This is again we have in the denominator c squared minus u v squared. Right. Now remember that all of this thing was equal to 1 minus 1 over c squared times v minus u over 1 minus v u over c squared, right? This is where we actually started off. Let me go back over here, right? So what we are doing is we are simplifying or solving this term over here, right? Okay, so the goal is then to eventually put it back in this term over here, right? Okay, in my gamma plus, right? Okay, so well, now actually there is a square up here, right? Okay, so now let's just put this back in our gamma plus, right? And so let's do that over here. So we have gamma plus will be now, after putting this back in there, would be equal to, let me actually go back to gamma plus, right? So this over here is your gamma plus, right? Okay, so you can see that it is the inverse of this quantity that we just simplified or solved, right? And this the quantity has a square root on top as well. So we would have to then take the square root of this thing, right? And inverse it, take the inverse, and then write our gamma plus, right? Okay, so let's do that now. So the inverse would be first c square minus uv, right? And the square root would get rid of this squared up here, right? Okay. Then in the denominator, we would have this term that was over here in the numerator, and we would square root that term. So let's go ahead and do that. So we would have c power 4 minus u squared c squared plus v squared times, let me put this in brackets, plus v squared times u squared minus c squared. So it is the same term that is over here. I have just rearranged some of the terms here and there, right? And then this over here would be equal to, let me actually do it on the next page, right? But let me say what I'm going to do. I'm going to take c squared common from here, and I'm going to do the same thing. I'm going to take it common from here. So we can get this original Lorentz factor type term, right? So the original gamma type term. Okay, so let's go ahead and do that mathematically. And so what that would be is then the gamma plus would be equal to c squared, taking common outside, I would be left with 1 minus v times u over c squared, bracket closed, over square root. I would take c square outside. Actually, I would take c power 4 outside, right? Let me take c power 4 outside, and once I do that, in that way I would get inside 1 minus u squared, right? U squared over c squared. So now I got this term that is, it looks like the Lorentz factor, right? And then of course I have another term that is plus v squared over c4, and let me write this, but expand the square root, right, because it's over all of this term. And then of course I have in brackets u squared minus c squared. Right, so from here we can then simplify this a bit more, right? And I write it as, because you can see that we have this c power 4 being multiplied here, and we have it divided over here. We could just actually factor it out, and we could get rid of it, right? Okay, so let's go ahead and do that. So we would have gamma plus would then be equal to, if I take this c4, factor it outside from below, right, in the numerator, and then of course because it has a square root on top, all of this expression in the denominator, c4 would come outside and it would become c squared, and then it would then go away with this c squared, right? Okay, and so then the expression would become 1 minus v times u over c squared over under the root of 1 minus u squared over c squared, right? Because we factored the c4 out, c power 4 outside, so we would not have that, and we would have inside over here 1 minus v squared over c squared, right? Okay, so now we can write our gamma plus as in terms of the Lorentz factor gamma, because we have that down here. So what that would be is now my gamma plus would that be written as gamma times 1 minus uv over c squared over under the root 1 minus u squared over c squared. Right, so this over here is then my gamma plus, right? So I have figured out what my gamma plus is, and again let me mention that u is the velocity of the charge q, right? Okay, so now in the similar manner we could compute gamma minus, but I would not do that over here because the calculation is very similar, or totally actually similar to what we just did for gamma plus. So you could do that as an exercise for yourself, which would be a good exercise, right? So this is then equal to gamma minus is actually equal to gamma times 1 plus uv over c squared divided by under the root 1 minus u squared over c squared, right? And so this over here is then your gamma minus. Right, now again recall that we wrote our total charge density. Let me write it down here again. The total charge density was simply the sum of your first you had lambda naught outside, and then you had gamma plus minus gamma minus, right? So it was the sum of your charge densities, lambda plus and lambda minus, and then we wrote it in terms of your lambda naught, that is the charge density of the wire in its own rest frame, right? Okay, so now all we have to do is from here is substitute the expressions for our these gamma minus and gamma plus, right? So gamma plus over here and gamma minus over here. So these expressions are going to go in this equation over here, and so we would get our total charge density. So let's go ahead and do that, right? So your lambda total, or the total charge density, would then be equal to lambda naught over under the root 1 minus u squared over c squared times 1 minus uv, let me write it down properly, this is u, this is v, over c squared, minus, for your gamma minus you had 1 plus uv over c squared, right? And then let's close these curly brackets. Now all we have to do is simplify this term over here, and that would obviously simplify to, let me write it down, total charge density is your lambda naught times, I forgot to write this gamma over here, right? So lambda naught times gamma over under the root 1 minus u squared or v squared times, let's solve this expression. So you have, in this expression you have a 1 and this minus sign and this 1, so that would go away, and then you have negative this thing, and this minus when distributed over here, that would become negative as well. So 2 times negative of this, so then that's negative 2 uv over c squared, right? And so this is your total charge density, right? Okay, so let me box it, right? Because this charge density is actually extremely important because of the fact that this charge density is now going to create an electric field in the S prime frame, right? So that is now the frame of the moving charge. And so that electric field would be then E prime is equal to the total charge density over 2 pi epsilon naught times R, right? And so this would be the electric field created due to the charge density that we just figured out. That was the total charge density, right? Okay, so in the S prime frame, there is then an electrical force on charge Q, right? And that's pretty obvious because we have electric field in that frame, and so we are bound to have this electrical force on that charge Q, because the S prime frame is for charge Q. Keep mentioning that again and again, right? So if you recall from your electrostatics, right, that your F is equal to QE. So for the prime frame, F prime is equal to Q times E prime, right? And now all you have to do is then substitute the value of E prime, and so then you would get F prime. That would be your Q lambda total, that is the total charge density, over 2 pi epsilon naught times R. Very nice. Okay, now all you have to do is substitute the value of total charge density, and so you would get your force experienced by the moving charge Q. So Q over 2 pi epsilon naught R times negative, all I'm doing here is substituting the value of this total charge density. Let me go back and show you that. This was this thing over here, right? Right, so let's do that. Negative 2 times uv over c squared times lambda over under the root 1 minus u squared over c squared, right? U squared over c squared, right? Okay, so then this is the force that is experienced by the charge Q. Now if there is a force on the charge Q in the S prime frame, then there must be a force in the S frame, which we may compute directly by using the transformation rule for the forces, right? So let's go ahead and let's do that, yeah? Okay, so now let's quickly first recall the Lorentz transformation of the forces, which as usual I will take in the direction of motion, that is along the x-axis. So I'm assuming that the charges are moving in the x-axis. So I would have that then for my fx primed will be equal to fx minus beta, and beta is simply v over c, right? Let me write that down over here. Beta is v over c. So beta times u dot f, right? Your original vector for force over c, right? Right. And then you would have 1 minus again beta times u in the x direction, right, over c. So this is the Lorentz transformation for the force along the x direction. And let me again mention this, that I'm assuming that the charges are moving in the x direction, right? And so for that, then my fy transformation would be equal to fy over gamma times 1 minus beta ux over c, right? Okay, and last but not the least, f prime z would then be equal to f along z direction over gamma times 1 minus beta ux over c. Right. Okay. Now, since the charged particle is at rest in the s prime frame with respect to the s frame, so vector u is going to be 0, right? So this thing is then 0, and then obviously if this thing is 0, then so is my u in the x direction is also 0. Okay, so from here now, first let me go back or go forward to the next page, right? So from this now we have my fx prime is equal to fx because I have substituted for ux being equal to 0, and so is my vector u, so in this equation, right? Okay, so then that gives me my fx prime is equal to fx, and my fy prime is equal to fy over gamma, right? And my fz prime is then equal to fz over gamma, right? So all I have done is I have substituted for u vector and ux being equal to 0 from here, right? Okay, so let's go back here. Now you can see that the parallel components of your f prime are simply equal to the untransformed parallel components of f, and the perpendicular components of your f prime are equal to 1 over gamma times f prime, the perpendicular components again, right? Okay, so then the component of f parallel to the motion of s prime is unchanged, right? And whereas the perpendicular components are affected by a factor of gamma, right? So we can see this from this equation or these expressions over here, right? So the parallel component was in the x direction, my particle is moving in the x direction, but y and z are then perpendicular to that, and so the perpendicular components are affected, right? Okay, so what that means is then my f is equal to 1 over gamma f prime, right? And so with that now, with this, what I have is that I can go ahead and recall the f prime as I previously found out, right? What was that equal to? Let me actually go back. Yeah, it's over here, right? So this expression over here, we are going to use this expression now. So let me write this down again over here. So my f prime is was equal to q over 2 pi epsilon naught r times the negative 2 uv over c squared times lambda over under the root 1 minus u squared over c squared, right? And now let's close these brackets. Okay, and gamma over here is now 1 over under the root 1 minus u squared over c squared, right? Before I wrote gamma as 1 over 1 under the root 1 minus v squared over c squared, but in this case it would be instead of v squared, I would be having u squared, because if you noticed previously over here, I wrote my expression as such, right? So instead of writing f prime is equal to 1 over gamma times f, I wrote it like this, okay? So now with this, all I have to do is substitute for gamma in this equation, that is over here, this one. So f is equal to 1 over gamma times f prime. So f is equal to 1 over gamma times, let me actually write q over 2 pi epsilon naught r, again curly brackets, negative 2 uv over c squared times lambda over under the root 1 minus u squared over c squared, right? But we know that gamma is this thing over here, and we have this term over here as well, right? So what we could do is then gamma would cancel out with this term over here, right? Because again, note that this term is in the denominator, and your gamma is 1 over, or the inverse of this term, and so it would cancel out with this term, right? Okay, so if it cancels out, then all we are left with is q over 2 pi epsilon naught r times negative 2 uv over c squared times lambda, right? Let me write that down now. So what that is that my f is equal to negative q u 2 lambda v over 2 pi r, and I can write this term constant over here, epsilon naught c squared, right? 1 over epsilon naught c squared, right? Now what this equation becomes, if you know what your mu naught is, right? This equation is now f is equal to negative q times u, and the rest of the expression is mu naught I over 2 pi r, right? So this equation is this equation right here, right? Now if you recall from magnetostatics, that the Biot-Savart or Biot-Savart, I don't know how to pronounce that, their law states that your magnetic field B is mu naught I over 2 pi r, right? And so then with this thing, my F is equal to negative q times the velocity u, and this thing is B, right? So, well, it didn't really matter if you recall that B is equal to this equation over here, right? This itself is then the magnetic force, right? And over here it is the magnetic force that you most commonly know, right? So that is F is equal to negative QUB, which is the magnetic force. And so we derived the magnetic force between a current carrying wire and a moving charge Q without ever at all invoking the law of magnetism, right? And so to me, this result is extremely beautiful, right? As it tells you that indeed the magnetism is one of the marvelous wonders of nature, right? Okay, so that's it for this video. I hope you enjoyed, and I hope you gained some knowledge as well. And I hope you find it equally extremely beautiful, the result that we just figured out, because to me it is absolutely marvelous.